Okay. Good morning, everyone. Is there anything to ask? Okay, as far as the grading, I have not done any of the grading this week because I was really busy with the kids to set them for the schools, and that was the first week of school for them after that spring break and just shut down the classes. So I'm sorry I haven't touched it, but I will probably finish everything by this weekend. And that's why you don't see the solutions for the test up there. But do you have any concern, anything? Because I haven't received any email except just 2 emails from students. I feel it was just really smooth and no one has any problem with doing the test in this way, or anything that you concern about. Anyone can share anything if you have. No, we're good. So the Jordan Canonical Form is just continuing what we call diagonalization. So we have had diagonalization. I'll review what we have. Even we will try one example again to see what we've seen it. If you don't remember, it was just 1 week off. And I hope you have had really safe, healthy week. This week was just really a resting time for most of us, and it was just no homework, no assignment, nothing. So that was just really to catch up with whatever you have had at home with your family. So then we don't have any assignment this week too, because it's just really a long discussion to be ready for the homework or the problems. I have to cover a few things, concepts, terminologies, that then you are ready to do your assignment. The only thing is just that quiz, weekly quiz, which is just really based on 5.2, not really anything about this Jordan Canonical Form. But again, the discussion is really continuing the same thing that we have had in chapter 5. That's why it's here. And then I don't think you can follow from the book for this part of lecture that I want to do in 3 sessions. 3 sessions. One is today, and then Wednesday, and then the next Monday. So it's better to just really pay attention what I have here, and that would be really enough for us. And then plus a few homeworks that you have from 7.1 and 7.2. So then again, I don't recommend you to go back to look at the book, because that's just really more abstract concepts that we don't know. We just need to know the computation, how it's related to the organization. So one more time, if we have had any if we have had any transformation and the goal is to make it any transformation and the goal is to make it diagonal, whether it's diagonalizable or not. So it was just really making a basis that the corresponding matrix is diagonal matrix. Okay, so we are looking for a basis that the corresponding matrix transformation is going to be a diagonal matrix. How we can find it? Actually, we figure out, okay, if we just really get the eigenvalues of that matrix and then corresponding eigenvectors of that matrix, so that's just really the basis that we are looking for. So the basis that we are looking for is really the set of eigenvectors of the matrix transformation. And then the question was, if we haven't had enough eigenvectors, so if it is a 3 by 3, I need really 3 eigenvectors to get that basis. And if it is a 2 by 2, I need 2. If it is a 5 by 5, I need to have 5 eigenvectors to get that basis, or to call my transformation to be diagonalizable. Okay, so then the question was, okay, how about if I don't have enough vectors? So how about if it is a 2 by 2 and I get the repeated eigenvalues? So then that's just not diagonalizable anymore, because it's just only one free variable. How do I make the missing one? We have had some ideas in the previous course when we were solving the system of differential equation by using eigenvalues, but this is just really, I will say, somehow remind you all the formulas that you've seen there, and you just see why we write it in that form. So why was just really some power going there. So then the same topic, the same questions was about the matrices. If you have the diagonalizable matrix, means you have enough eigenvectors for that matrix. And then if you don't have enough eigenvectors, what would be the next step, or what is how you can jump to make enough. So how you can make the enough eigenvectors. I have tried one examples. This is just from last time. So this is, if it is a 3 by 3 and you got 3 eigenvalues, one of them is repeated, which is right over here. So if it is repeated, lambda equals 1 2 times, and as long as I get just really 2 free variables right over here, this is perfect. But if it's not, then I just have to make another one. So I'm just missing one of my eigenvector to just diagonal my matrix. So this is, so how do I make the missing one? It's fine. We can just go to the more power of a minus lambda I, right? So that was just what we call generalized eigenvector. To generalize my eigenvector, all I need to do that null space of a minus lambda I. Now you need to just jump to some other power. So it just really depends on how many do I need. So what is the P? I don't know. It depends on how many do I need. So if it is just really a 3 by 3, like right over here, which I'm missing only one, and then I need to just make one more eigenvector, so the second power would be enough. So that's just really depends on the size of your matrix to know how many P or how big is your P, the power that you need to make. And that's just really a little bit confusion about choosing the vectors, because when we go to the second power, some of them is really clear. So like this problem was just easy. So some homeworks is like that. So lambda equals 1 was my repeated one. I expected to get 2 free variables. I did not. So then I had to raise it to the second power. So then when I just made that null space, I have had one of them, which is just really from the previous computations. And that was just what we call regular eigenvector. The other one was just a brand new. That's just what we call generalized eigenvector, okay? So that's just all. I will say somehow this is happening, but I will learn another terminology if this is not directly right there. Okay, so then how do I make it? And that's why I add one more example here to just say this is not really always right there to see, okay, I have had one of them is from the previous step or the regular one, then the other one is going to be the missing one because I need to have two of them. And then for the same matrix, because I have had two already, one from regular, one from generalized one, and then this is just really the third one, because the lambda equals 3 was just the other eigenvector. So this is going to make the Q, right? The order matter, obviously the order matter. So what we are going to call Jordan Canonical Form is kind of diagonal. So a kind of diagonal, so means I have my eigenvalues right there. But since one of them was coming from the generalized form, so this is going to be, oops, something happened. So this is going to be my corresponding column for what we call generalized. Something is changing my notation. Eigenvector, okay? So I'm just really noticing what's going on is diagonal matrix, and there is a 1 on top of whatever is generalized, okay? So since your middle column from the Q, the middle column, it was just a generalized one, so then your middle column has that extra one, okay? So that's just really what we call Jordan canonical form. Sorry, this is not really what we call diagonal matrix. Again, this is reminding you, this is not really what we call diagonal matrix, because this is all the way lambdas, but it does have 1 on top of each lambda, okay, except the first one. That's actually telling me if you have had so that's just telling me if there is just really columns in my Q, this is going to be my regular eigenvector. I mean, your first column is regular eigenvector, and then from here to here, these are going to be generalized ones. So that 1 on top of the lambdas is the sign for generalized one. Okay, so specifically, I don't know how many n by n I have over here. So it doesn't matter what is n by n. It says only I could get 1 free variable from regular computation, and then I had to go to the power of n minus 1 to get the others. Okay, so that is telling me how many more power I need to have a minus lambda I to get the rest of my eigenvectors or generalized eigenvectors. Okay, so this is the form of Jordan canonical form again. So you might have blocks for each eigenvalues. So if the size of block is 1 by 1, so means you have one eigenvalue, multiplicity of 1, and corresponding one eigenvector. But if you have some blocks which is more than 1 by 1, so means you got 1 from the regular computation, but you had to extend it to the more power of a minus lambda I to get the rest of them. Okay, so this is just from the last class. Is there any question from this review? Do I have any question here? No? Anyone else? Any question? No, right? One more no helps me. Okay, thank you. So then I go to the another example from the same section, just to remember what was the process of computation. So it's really similar to what you call eigenvalue. So it just really one more power. So this is just one example from 7.1 part C, problem number 2. So which the matrix is just the only thing that is provided. The only thing that we have is just the matrix of 3 by 3. And it asks us to find, so it is just really looking for the bases consist of that generalized eigenvalues and eigenvectors, and then it asks us to make it in Jordan canonical form. So make the matrix to be in Jordan canonical form. So what I have done is just make the determinant of a minus lambda I. This is just to remind you, okay, that's a process to get the eigenvalues. So this is just really by computer, I got the eigenvalues is -1 and then 2 and 2. And then determinant of this is my characteristic polynomial. And then these are the roots. So -1 and then 2 and 2 are the roots. So for -1, it's just really multiplicity of 1. All I need is one free variable, one eigenvector, then I'm good to go, right? So for the first one, which is lambda equals 1, all I need to just have one free variable, and then I will get corresponding by that one eigenvector, and then that's perfect. So that's not the problem. For 2, because the repetition is 2, when I try to go by just the first power, so just the null space of a minus 2 I get only one free variable, and corresponding by that, I just get only one eigenvector. But since the multiplicity is 2, I just need one more. So what does it mean? Means I need to go to the next power of a minus lambda I, which we call it generalized eigenvector. So I will find the null space for not a minus lambda I for one more power, because I need one more free variable. So that's just really squaring and make it row echelon form and just get the free variables. So there are 2 free variables this time. Okay, this is a good question to just really, this is good example to start whatever is the next concept. A little bit different than the previous problem, because for the previous problem, if I go back to the next, let me just go back all the way to the previous example that we tried. There was just really nice one. Why was a nice one? Because when we tried to make that second power right over here, so when you have tried to make it second power, what you got was exactly your regular eigenvector after factoring your free variables, and then one more, which we call it generalized one. Okay, so the first one right over here, which is 1 0 0, was really coming in first step right over here, which is just really regular one. So we have had the regular one right after squaring. Okay, So, but this example is just really to start the next concept, to say, okay, seems this is something different, right? Because my regular one is 111, my regular one is 111, but when I made it this row echelon form, I got 120, and then I got 102. Is there any question about this? So I just made it the first power, which was only one free variable. Then I solved it. I got one eigenvector. And then for the next power, I got two free variables. I factored it out. So that gives me two different. What this is not really repeated. If it was really like a previous problem, I expected to have the first one to be 111 and the other one to be something different, to call it generalized one. Okay. So this is just really the thing that I have to notice to just define what is the next concept, which we call it cycle. So I explained it over here, but I will come back to this example again. So I will say this vector of 120 is just the start point. And since you have a minus 2i of whatever vector is just really what you are looking for, null space, I can't go further because as I know, a minus lambda I to the second power for these two vectors that I got for this step is going to be always 0, because that's just really how we define, right? So the v itself, either number 1 or number 2, the v itself is coming from my null space. So obviously null space of a minus lambda I to the power of second. So obviously I've plugged in any of them to more power is going to make just 0. So, but I can't have in basis 0, so that doesn't make sense. That's why I go all the way to 1 power less than the null space that I was looking for. So that was a square. I just have starting point is 120. The step before is going to be a minus lambda I to the first power of 120. Okay, so this is the concept we want to just learn today. Then it's just going to be 120, and then when I have a minus lambda I did the computation over here because that's my a right over here. So I just multiplied it by 120. So that gives me really like 9 minus 4 times, right? 4 times 2, and then 21. That's the second. I can't have my mouse when I'm pointing somewhere, I believe. So let me go to the annotate, select this one to see whether still I have, no, right? It doesn't work anymore. When the annotate is active, this my pen doesn't work anymore. But that was good, at least you could follow my pen. Okay, anyway, it doesn't work. We have to go back. So what's going on over here? I got 120, which was coming from my generalized form, and then when I just really multiply by a minus lambda I got 111, right? Not really the what was the direct computation was just really 111. I had to multiply my generalized one to a minus lambda I to get that one. This is just brand new. So this is just a start point 120. Why did I select 120? Is it any different if I just start from 102? So the answer is no. I could just really start from one of these generalized eigenvectors that I got and see whether I get back to the regular one or not. So that's it. That's the only thing I need to notice, right? So I have started from 0, which is the first one on this, and then when I just distribute a minus lambda I, that gives me the old one, the regular one. So then I'm good to go because that's just really making the Q. If I call it Q, it's better because that's how we call it in this book or this lecture note. So then I have had one from the first lambdas, right? So this is coming for the eigenvalue of lambda equals -1. That's 130. This is coming from lambda equals to, from regular computation, a minus lambda I, null space of a minus 2I. And then this is going to be the generalized one, right? And this is generalized eigenvector for what is lambda equals to. So then again, one more time, if I'm looking to this piece, it says -1 is sitting in the first column, and then 2 is just right this. These are really diagonal, but this one right over here, this is telling me my last column. This is telling me my last column is my generalized eigen. So again, it looks nice. It's not really completely diagonalized or diagonal matrix, but it looks really nice for multiplication or power. For the, that's what we call Jordan Canonical Form. Usually I use this notation because that says the size of the block is 1. The size of the block for lambda equals 2 is 2, which is the multiplicity of your lambda equals 2. Any question about this computation?
Yes. So if we chose 102, would there be a chance that it does not give us back our original?
That's a very good question. We can just try it right over here. So because if I multiply by 9, I don't care what is the middle one because the middle one is 0. I don't care what is the middle column because it's the 0. I haven't tried it, so but I believe should be the same. Okay, times 2, and this is 21 minus 11 times 2. Do you see what's the numbers is coming out? Do you see or no?
Yeah.
So the number is coming out with the -1, -1, -1, which is perfect. So the
We
answer,
would use -1, -1, -1 instead of 1, 1, 1.
I will say, just remember any scalar multiplication as long as eigenvectors is fine, right? So if you just say 1, 1, 1 is eigenvector, any scalar multiplication of 1, 1, 1 is eigenvector. But since we have started originally with 1, 1, 1, what happened if I go by -1, -1, -1? So the problem is this comes to the +1. So sorry, let me just say that was corresponding by this one. Sorry. So this is just, instead of being like the block of 2, 2, that goes to the -1. No, it's not fine. You have to keep it as 1, 1, 1.
Okay. Thank you.
Still is fine as far as, because the goal of this kind of diagonalization is just really make it in a power just easier when you compose too many times with just the same transformation. That's just handling easier, but still is fine. But negative is just really something that we don't like it. We prefer to be in this form. Okay, so but still, but I call it still is Jordan Canonical Form, but that's just what we don't like it. So that's why we prefer really not preference, it's just really standard to be what was originally as regular eigenvectors. Okay, that was a good question. Any other question? Any other question? So for this part, I will really recommend you to have that calculation website. So fortunately, all of the exams is going to be take home and somehow open note. So you're using your lecture notes. So then these computations of really, because you know what's the goal, right? So if you're it's right over here. So you have to really try on your on your calculator or your computer to see whether if you have Q inverse A times Q, you really produce what you call Jordan Canonical Form of your. So that's just really what you need to test after each computations. Then you will figure out whether you made any negative wrong, whether sometimes because you might just really switch these two columns. In the previous chapter, it was perfect, or switch this by this, switch this by this, okay? So in previous chapter, the order doesn't matter. As long as you just really match the Q and Jordan Canonical Form or just diagonal form, you were fine. You could just put it in any order. But here I have to really be careful, because if I, so you can just right now try it on your calculator. If you try to switch this one, I will answer right now, Michael. So if you try to switch these two columns, okay, so then you can't produce your Jordan canonical form after Q inverse times A times Q. So then you will figure out, okay, not the right order. I have to really switch my columns to make that one, okay? So computations are really same, but the order here is matter, okay? So if you just reorder your lambdas in each column, so then you might not get that Jordan canonical form that you claim to get right over here, okay? So then just you have to somehow switch and see which one gives you right Jordan canonical form. That's a good question. Is the gamma to be my basis? Actually, I need 3 vectors to be my basis, right? So yes, the gamma is part of my basis. And then if I add the gamma is part of my basis, this is number 1, number 2, right? So you got 1 and 2. So if I just use the highlighter, so you got 1 and 2, which is just perfect, but you need one more, which is right over here, or it's just really this one. Gamma is, yes, gamma is part of my basis plus whatever is missing, right? Because it's really 3 by 3, it needs to have 3 of them. So what's the basis? If the question asks me to find the basis, it was just 130, 111, 120. Thank you, Michael. I forgot to write it over here. Okay. Any other question? Any other question? Okay, so again, as I said, this is a fact that I have to remember. If you have any characteristic polynomials and you got your eigenvalues, so means your polynomial can be factored out or it's split. So then this means you have the matrix of A similar to your Jordan canonical form. So which your Jordan canonical form, again, has to be really the form that you claim, okay? Because you could just really write this Jordan canonical form in any other order, right? So you might say this is really same if I write 2, 1, 2, and then negative 1 here. There's nothing wrong to be in this order, right? This is still a Jordan canonical form for this one. So you could reorder it, but that just the claim of whatever you said, this is my Q, and then Q inverse AQ should gives you whatever you claim to be, right? So then just really the matter of which order you put them. So then you have to switch this piece too, okay? Does it make sense? Make sense?
Yes.
Thank you. So linear transformation version of whatever we claim here for Jordan canonical form follows the same thing. As far as your characteristic polynomials is just really determinant of A minus lambda I. Here is determinant of the matrix transformation minus lambda I. As long as I know it's factored out or is split, so then there should be a basis always, either by the eigenvectors or generalized eigenvectors. So that matrix transformation is similar to the Jordan canonical form. Here, it's similar for matrix form. Here, for the transformation is really that Jordan canonical form. Okay, so that's just really difference between what we have had matrix version of Jordan canonical form and what we have over here as linear transformation to be in Jordan canonical form. So which means your corresponding matrix transformation in that beta basis must be in a form of what we call Jordan canonical form, okay? And that's just has a name, yeah? So the basis that you got is called Jordan canonical basis. The basis that you got is Jordan canonical basis, okay? What is the just really process of doing or finding this Jordan canonical form or this generalized eigenvectors to make the basis of the beta and the Q? Is really same process, right? So the main question is stays exactly the same way. I get the characteristic polynomial, step number 1. Find the roots of the characteristic polynomial, and then for each one, I try to make eigenvectors. If I'm just really fine, means multiplicity is the same as the number of eigenvectors I get, perfect, I'm done. But if I don't have enough, So then I have to extend the power of a minus lambda I, just try to make it generalized, okay? So then generalized eigenvectors is just really same process. When the first power of a minus lambda I doesn't work, so we just go to the next power to generalize whatever is your eigenvector, or to get the enough vectors that you expect to get. Enough vectors, again, when we have n by n matrix, we expect to get n vectors, right? So when you don't have the enough, means you don't have n many, right? So just terminologies, but the thing that I called gamma has a name over here. We call it cycle. So this is just giving you the terminologies in corresponding to the generalized eigenvectors. So it was eigenspace originally, right? So it was eigenspace originally when you have regular eigenvectors. So this is just the notation. It's called K capital K lambda. So that's just generalized eigenspace, huh? So this is a generalized eigenspace, and what it is just really the set of all vectors which instead of t minus lambda I times v to be 0, or instead of null space of t minus lambda I, this is going to be null space of t minus lambda I to the power of p for some p. So that's what we call generalized eigenspace. And then whatever was regular eigenspace right over here, whatever was regular eigenspace obviously is smaller than whatever is generalized one. So what does it mean? Whatever was eigenvector is a generalized eigenvector. Does it make sense? So p, because it says for some p, and p could be equal 1, 2. So if p is really 1, so that's just what we call eigenvector. So that then eigenvector is subspace of generalized eigenvector. Okay. And the other thing is, if you have that generalized eigenspace, this is a subspace. Okay, so that's just really showing you generalized eigenspace corresponding to the lambda is closed under addition, is closed under scalar multiplication. So closed under addition and scalar multiplication is really fine for any eigenvectors and for any generalized eigenvector. Okay, so that's just really showing why this is closed under addition, because I picked any two vectors, and then when it is in K, so in some power of t minus lambda I, the v1 v2 is going to be 0. All I need to do, just say that addition of the power of p1 plus v2 makes v1 plus v2 to be in null space of t minus lambda I. Okay, so then this is just really close under addition. Does it make sense? Do you agree with my close under addition? Should I?
Could you go over one more time, please?
Yeah. So what was the claim? It says if it is closed under addition, if I take any v1 and v2 from that generalized eigenspace, so then addition of v1 plus v2 must be in that generalized eigenspace. So since v1 is already in generalized eigenspace, so means for some p1, what is t minus lambda I to the power of p1, v1 equals 0, because this is just really telling me v1 is in null space of t minus lambda I to the power of p1. And then if the claim is v2 is in that generalized eigenspace, so means you have this power of, for some p2, the t minus lambda I to the power of p2 is 0. So then this means the v2 must be in the null space. So this is just really assumption. Okay, all I need to show, if I have v1 plus v2 still is null space of t minus lambda I to some power, which the claim is that power is going to be addition of p1 plus v2. Okay, so that's just what I'm trying to show, the v1 plus v2 in just null space of t minus lambda I to the power of p1 plus p2, which means just really split it out, because that's a linear transformation. I can just add it, just transformation of addition is addition of the transformation. since the t minus lambda I to the power of p1 for v1 is 0, so that gives me 0. T minus lambda I to the power of p2 for v2 is 0, so that gives me 0 too. So then addition is 0. Is that fine?
Yes, thank you.
Okay, same for scalar multiplication. So the claim is if the v is in this generalized eigenspace for some p, so then c times v, the scalar multiplication is there. So that makes sense because you can factor the c times 0, or any scalar times 0 is going to be 0. So this is closed under scalar multiplication. That makes that generalized eigenspace to be closed under addition, to be closed under scalar multiplication. So it is a subspace. Is the 0 there? Yes, that's what the claim was. We added the 0, right? So that's just okay for this, what we call k sub lambda. And then we will prove later. So if you remember, dimension of eigenspace, regular eigenspace, is less than equals multiplicity. If it was equal, so that was diagonal. If dimension of eigenspace is the same as multiplicity, that is a diagonal matrix. But for this one, that there's no condition. The dimension of this generalized eigenspace must be. That's just the whole process. We try to make exactly the same number of the size of the matrix, right? So must be the same as multiplicity. Does it make sense? So for the problem that we tried right over here, which was lambda equals 2 with the multiplicity of the 2, so we must get 2 eigenvectors. One of them is just regular, the other one is generalized, but that's just really saying the dimension of this null space is going to be 2. The dimension of this null space is going to be 2. Why? Because the multiplicity of 2 is 2. Does it make sense? Okay. So I have some example. I mean, this is just really two things that we need to notice about. One of them is the good news. The other one, I call it bad news. The good news is whenever you have had any type of the process that is just really try to get the a minus lambda I, set it equals 0, determinant equals 0, and get that what is corresponding eigenvectors. For generalized eigenvectors, for the property number 4, it says lambdas always carries its weight. What does it mean? If I have eigenvalue repeated 2 times, so then eigenspace corresponding by, generalized eigenspace corresponding by that has 2 dimension, and this is perfect, right? So that guarantees always the number of vectors that I get from generalized process of eigenvectors is going to give me always the same number of the multiplicity. So then this is fine. The bad news is the basis that I have made, the way that I have selected to be just really that V. I go back again one more time what I'm talking. So the way that we just have this basis, part of basis to be first V and then A minus lambda I of V. So this is just a confusion over here for selecting my generalized eigenvector and make it in Jordan Canonical Form, okay? So to get that basis, to have a Jordan Canonical Form, we must really be careful. So how did I select my eigenvector, and then how did I make my generalized eigenvector, okay? So what do I mean by be careful? I just explained right over here, wrong answer and right answer, okay? So this is just really the process that you might get wrong answer, and then in next page you will have the right answer. So this is a wrong answer. What's going on? There was a transformation given to me. What was the transformation? Gives me for any function derivative, first derivative plus the second derivative. So for now, I have started from the standard basis of 1x, x squared, x cubed for polynomial of degree 3 or less. So then I have made my corresponding matrix transformation for this standard basis. So transformation of 1 is the derivative of first derivative plus second derivative, so it's 0, so that makes my first column. Transformation of x based on definition says first derivative plus second derivative, so first derivative plus second derivative is 1, so this is my second column, so on, right? So the second x squared, the first derivative of x squared, second derivative of x squared, so that's my next column. And then for x cubed, first derivative of x cubed, second derivative of x cubed, and that gives you my last column. Okay, so this is my matrix transformation in a standard basis, right? So what do I do is just really clear to see all numbers on this column, sorry, in this diagonal is going to be 0. So if you make determinant of a minus lambda I, you will get lambda equals 0. Does it make sense? So the only eigenvalue for this matrix is 0, so it's repeated 4 times. Fine? So lambda equals 0 has the multiplicity of 4. What does it mean? So that means the dimension of the generalized eigen space is going to be 4. What does it mean? The whole space has dimension 4. The whole space has dimension 4, right? So means your eigenspace actually is the entire space of polynomial of degree 3 or less. So this eigenspace or generalized eigenspace for lambda equals 4 has the same dimension of the entire vector space of polynomial of degree 3. So should I say, this is a wrong step. Should I say, okay, I was looking for a beta, that's my beta. Standard basis is my beta, and that's just my generalized eigenspace. Because what was generalized eigenspace? Polynomial of degree 3. So this is just really the basis for polynomial of degree 3. So this means every single element of your polynomial of degree 3 is going to be a generalized eigenvector. And then this is a wrong process. Why? Because I can't call that basis, because the form that you have for your matrix is right over here, right? So this is your matrix. Is it in Jordan canonical form? No, it is not. So this matrix right over here is not Jordan canonical form. So that is not the beta that you are looking for. So you have to really be careful about the process. Seems really correct, but that's not the beta that I'm looking for. So beta that I'm looking for must make my matrix in a form of Jordan canonical form. But this is not in Jordan canonical form, okay? So that's just really remind us, you have to be careful about the selection of your bases. So your basis is not really what you have started with. It is just really a process of making eigenvalues, making corresponding eigenvectors, which we skip over here because wrongly we stop somewhere here, right? So that's just making eigenvectors, and then to see how many free variable do I get. If I don't get enough, which I won't, so then I do go to the second power of I minus lambda I, third power, and fourth power of I minus lambda I. And this is a really good example because of the dimension of eigenspace is really same as the dimension of entire, and wrongly we might think, okay, so I got my basis, I'm fine, right? But that wasn't true, because the original matrix is not really in form of what we call Jordan canonical form. Does it make sense? Is there any question? Can you please add your questions or comments here? Any question here? Can you please tell me, anyone is taking notes right now? Should I slow down or I'm fine?
Can you slow down just a little bit?
Okay.
Thank you.
You're welcome. Okay. Any question here?
Okay, so in the context of this problem, how do we know like which generalized eigenvectors should I choose?
That's the next, yeah, that's a good question. This is just continuing. Yeah,
Oh,
because
okay.
even, you know, what's the problem here? Even we haven't started to find any of the eigenvectors, right? Because we did not make the null space. We did not make the null space of A minus 0I and then try to make it row echelon form and try to make the free variable, try to make the V, okay? So that's just really what we are missing here, because we were happy about to get the dimension of eigenspace exactly the same as the original vector space, and then we stop. Okay, so this is the beta that we have. Okay, so this is just really what we need a terminology, because before doing that problem to choose the right one. So the terminology that I have tried in the first example, and this is just the second example that we made it wrongly, was the cycle. Okay, so what is the cycle of generalized eigenvectors? So the cycle says, as long as there is a transformation when lambda is your eigenvector, so there is a transformation, lambda is eigenvector, so then you just find the smallest power of the p that t minus lambda I to the power of p equals 0. Or just again means the same as v is in the null space of t minus lambda I to the power of p for smallest possible p, right? So then these things that I call it gamma, it has a name. We call it the cycle for generalized eigenvectors. So we start from one vector, we start from the one vector, and then we go to the first power of that to go to the next power to the next power. Sorry, this is a p. So we go to the next p minus 2. Oopsie. P minus 2. So for the example that I tried, I have had only 2 of them. So if you remember, I have started from v, and then the other one was t minus lambda I to the v, and then that was my gamma. So because I have had really the multiplicity of 2. So what is the size of the entire basis is just a cycle for now, but later is going to be part of my basis. So what is the size of, or how many of them do we have, is just really p many, right? P many vectors is there. That's why we call it the cycle generalized eigenvector corresponding to the lambda of the length of p. So what is the p is just really the smallest power that you get the v inside of that. So what I have had in that previous example, 7.1 problem number 2 part C, was just really what we call a cycle. Okay, so cycle is whenever you have a generalized eigenvector, is not entire eigenspace, is a part of your eigenspace. There are many facts about this cycle that we have tried. So for example, first fact is, if you start from one vector and just make it to the t minus lambda I of the same vector, and then going to the next power and the next power until the one power less than whatever is just your smallest power of null space. So the first one is always your eigen vector. So initial vector is always your eigenvector. The first one is always your eigenvector. I can go back one more time to say what I'm talking about, because I have tried this example. So this is just really the same thing that I have tried over here. So that is a cycle for lambda equals 2. So this is just really end vector, and this is your initial vector. My claim is this initial vector is always my eigenvector. So if I got this one to be really my regular eigenvector, it wasn't really accident. It's always true. Okay, so the first vector to be always your eigenvector, regular eigenvector, is not accident. This is just always the process of being a cycle. So wherever you start, so the first one or the highest power before the p is going to be my eigenvector. And then I just gave you a really short proof why the first one is always eigenvector. So this is just really the proof right over here to tell us, okay, so why the first one is always eigenvector is just really easy to show, okay? So don't worry about the top one, is just really being over here. When you have transformation of p to the power of 1, again, so to remind us what we call eigenvector. So the claim is t minus lambda I to the power of p minus 1 of the v is eigenvector. Okay, so my claim is my first thing in the cycle is going to be my first thing in this cycle, which is right over here, is going to be my eigenvector. And this is just the proof, because that t minus lambda I to the power of p minus 1 is just really distributing t inside. So distributing t inside, that gives me one more power of p, and then plus, actually this is minus because I have distributed because of this. Okay, so this is minus lambda, and then I have t times I, t minus lambda I to the power of p minus 1, which gives me 0. So which gives me this part is 0, and that gives me lambda of the same thing, okay? I reminded why this is going to be eigenvector, because if you have t of something, lambda times of the same thing, that thing is going to be eigenvector. That's what's happening over here. T of something, which is t minus lambda I to the p minus 1 equals to lambda times of the same thing. So this is just really telling me the first one must be always, what I did over here is just really distribute. Okay, so I did just really distribute this inside and this inside. That's what we did over here. And that gives me the transformation of t minus lambda I to the power of p minus 1 of any v is going to be eigenvector. So this little short proof is really to show the claim of the first one is always eigenvector. Is there any question? Let me just show you this part. Any question here?
How did you get the second line? The line after the t of t minus lambda I p minus 2.
This is t of the process is t of the first thing. Okay, so which is p minus 2 plus 1, because it is a power of 1, so that gives me p minus 1. And then when I have a lambda, again this is a minus because this is a minus, and then I, so then this is just t times of I, which is just really same thing, t minus lambda I to the power of same power, and is really same thing over here. So when I have t of t, since it was p minus 1, so it's p minus 1 plus 1, so that gives me p, and then when I have this to this, it's just really lambda of whatever left. Does it make sense?
I don't seem to understand how are we going from t to the, how are we distributing t to the lambda I? I don't follow that.
T to the lambda I.
Because you drew an arrow from t to lambda I. I don't follow that part.
Let's just go one more time. It's going from here, t to the lambda I, And that gives me a constant, which I factor it out. And then I have I, and then t minus lambda I to the power of p minus 1. No? This is distributing to this. And it's right there.
Yeah, that's the part I don't get.
Can you write on my part? I think, can you write, can you try, do you have iPad or something to write?
I don't have an iPad or anything.
Okay, I was wondering if you can write something, why this is unclear.
Your screen.
Uh-huh.
Anyone can annotate on your screen. If you're using a computer, on the view options top part, there's an option to annotate, and then we can write on your screen and everyone can see it.
Yeah. Okay. So his question is why t of t minus lambda I and then to the power of p minus 1 of the v. So you don't have any problem with the first piece?
Yeah. Because it looks, to me, it looks like, actually, never mind. Yeah, because for me, like, it looks like it should just be t minus lambda I to the p. And then I just don't understand that second part. The second part.
But they're really similar. Why, if you are agree with the t times t, one of them is just really power of 1, the other one is p minus 1, so that makes
Right.
it the total of p. So
Right.
this is just really because t times I mean I is nothing, so it's just really t of that minus lambda I to the power of p minus 1. Okay, so the only thing is that we are doing over here we do have tt, but here we just have I. Okay, so then we just ignore the I, and then we have whatever was originally, because I doesn't do anything on my transformation. Am I right?
Oh.
If you are fine with this process of making p minus 1 plus 1 is just p, so the only thing is just your I is nothing, right? So I is just really 1 in this process of transformation, so you left with whatever you have had because you have distributed that one. Is it fine?
All right. Yeah. Should be.
I think it's not this still, right, Solomon?
Huh?
I think you didn't get it. Your
Yeah,
voice is not. Yeah, your voice is not the way that you got it. Okay, so let's just see how we can. Okay, I will see.
We can move on. We can continue.
Yeah.
I can ask you on a separate day.
Maybe after class, we have finished the class. Okay, so we can stay a little bit if you don't have any class.
I have class at 10, so.
Okay.
Sorry.
So maybe the other day before the class, right? Wednesday
Yeah.
before the class. But I'll try to add something if I could, because that's just really something is missing. It's a very simple thing that is missing, but I will try to add some steps, okay? Let's just move on. What was it? This is just really the example that we made a mistake to choose the beta. We made a mistake to choose the beta in right over here. And so this is really same example, same transformation. So right now I want to, by using or learning what do we call cycle for lambda equals 0 and eigenvectors corresponding by that, I want to fix my problem. So this is the wrong answer. Now I want to fix my problem. So in order to make that cycle, the first thing is, in this example, we have had every single vectors to be generalized eigenvector, okay? And the generalized eigenvector, because of the dimension of eigenspace was just really 4, which is the same as the what is the dimension of the entire polynomial of degree 3. So then we want to select that eigenvector, the start point or the cycle, very carefully to get the cycle of length 4. Okay, so when we are looking for the cycle of length 4, what is the p? Okay, so what would be the p? So it has to be p4. So one less is going to be, one more time, if I go to the definition of cycle, so the smallest power of the p, the smallest power of the p, such that this is going to be 0, or v is in the null space of that power of the p, your cycle is 1 power less. So it means I'm looking for 1 power which is non-zero, because on basis I can't have the 0. Okay, so since the cycle has to be length of 4, why the cycle must be length of 4? Why the cycle of this problem, why the cycle of this problem must have length of equals 4?
My multiplicity is 4.
The dimension of eigenspace is 4, yeah. The dimension of eigenspace is 4, or the multiplicity is 4, is really. So that's just really same as saying what I'm looking for, the t minus lambda 1 less than 4, which is 3, has to be non-zero. Okay, so which means if your lambda equals 0, because for this problem all of the lambda was 0 for that example that we tried, so t minus lambda I to the power of third must be non-zero. Okay, so that's just really same transformation, same matrix transformation, times it 3 times. That's just right over here. This is what I got, right? Okay, when I multiply it by 3. Okay, so this process, if you remember, you have had it in the previous course. You have a start point. You start from something. Usually, if you remember in previous course, was either I or J or K. Okay, but here, because I have 4 dimensions, I have started from the 1. How do I know I must start it from the 1? Because the way that the transformation is defined, transformation was the first derivative plus the second derivative. So then if I just make it something that after a few many times of derivative I get 0, that's perfect. So the goal is you start from the v, and then transformation of the v, and then transformation one more time of the v. So transformation of one more times of the v. So the goal is, if you go a few times, so if you start from some point and you start to transform. So since the cycle is supposed to be 4, so this is 1, 2, 3, 4 of them. So that means after a few times, I expect to get 0. After a few times, I expect to get 0. So that's why I have selected to be x cubed. So when I have started from the x cube, so when I do the first transformation, so means, should I write over here, transformation of x cube was x cube prime plus x cube double prime. So which is just this thing over here. This is transformation of whatever is the result on top. So let me write it, is 3x squared plus 6x, right? So this is 3x squared plus 6x. So this is going to be 3x squared plus 6x prime plus 3x squared plus 6x double prime. Is it fine? So when I have v, which is the start point, and then I have the transformation of v, which is just really how it's defined to be the first derivative plus second derivative, and then I have the second one, so means just transformation of x cube is there. One more time, we transform that thing, which is derivative of the first derivative plus the second derivative. So that gives me this. let me write it down. So the first derivative of this one is going to be 12x plus 6, and then the second derivative of this one is just 12, right? Is it fine? Oopsie. Are you with me? What I'm trying to do, are you with me what I'm trying to do? Why is like this? How do I change it? Do you know why it makes it like this? Anyone has the...
What are you trying to do?
I can't write on my page.
Hmm.
It doesn't work for some reason.
You've got the marker selected.
Okay, so it should somehow go out, but it doesn't.
Are you sure you're not, this is your desktop?
Okay. I am sure what?
I was going to say, are you looking at the right window, like the OneNote window?
You mean I have two of them open? No, I don't.
Is Zoom, make sure the Zoom is minimized, right? Okay. And then, okay.
What happened? Oh, okay.
That looks pretty clear that that's OneNote. So then,
I have.
yeah, I would just restart OneNote.
Oh, something happened. Okay. No, it still is like that. This page is... Okay, finally. Let me just rewrite this part one more time. What I'm just trying to do is just explaining what was the transformation. So the transformation was defined to be, one more time. I'm just trying to write the steps. So if you are okay with I'm looking for the cycle to be length 4. So what's the goal is to start from some point and then take the, take the transformation a few times, take the transformation a few times, which that many times is just really get the entire cycle to be the size of 4. So means I have started from the x cube, and the main question is why x cube, okay? So the main question is why x cube. So when I have x cube, the transformation of x cube is going to be the derivative of x cube plus the second derivative of x cube. So that gives me 3x squared, and then this gives me 6x. So that's why you just have 0, then 6, and then 3. This is just because we have had the basis is just starting from the constant. And this is the next step, which is the t of x cube. And the t of x cube means you have had this, which you need to get the first derivative, and then you need to get the second derivative of this one. So the first derivative of this one is 6x, and then plus 6. And then the second derivative of 6x is just 6. So that gives me 6x. Oh no, just 6, okay. So this is 6x plus 12. So that's why you have the constant is 12, and then you have 6 as a first degree, and then no second degree, no. That's why it's in this way. So the next one is t of t square of x cube. and this is just really first derivative of this plus second derivative, which the first derivative is 6 and then second derivative is 0, so it's just only 6. So that's why you just have a 6 in here, and then this is a 0, right? So the cycle is just really starting from x cube, and then transformation of x cube, and then transformation of transformation, and then so x cube, transformation of x cube, transformation of the transformation, and transformation of transformation of transformation of x cube. Okay, so that's the cycle I'm looking for. That's the beta I'm looking for. It has a size 4. Yes, it does have a size 4. So it means there are 4 vectors in that. And then when I'm just trying to make the corresponding what is matrix transformation for this basis of the beta, that's exactly what we call Jordan Canonical Form, because that's the main diagonals. All lambdas equal 0, because lambda equals 0 was the eigenvalue for me. And then when I have this ones on top of that, that means I got only one original eigenvector, which was only 0, and the rest of them was generalized eigenvectors. Any question about the process?
Yeah. So if I took the original matrix transformation, it'll give me one eigenvector and only 3 more, right?
Exactly.
And then, so what another process to do this would be square it, find the eigenvector, and then cube it and find the eigenvector?
Exactly. So this is just really backward, huh? Since this is backward. So if I started from the whatever was the T transformation in a standard basis, right? And then the process was find the eigenvector, right? So how do I find the eigenvector? I just get the null space of T minus lambda I, and that gives me one free variable, right? So one free variable, that gives me really one free, one eigenvectors. So then I have to keep going to the T minus lambda I to the power of 3 to get 3 free variables and to get whatever is the leftover, right? So you just have one vector from the original one, you need 3 more. So yes, that's a good question.
Wait, so you do the original one and then you skip squaring it and you go to cubing it?
So this is a good question. Yeah, so you know how many do you need, right? So if I go back to the definition of the original, what we call general eigenvector, so that tells you how many more times, because if you, yes, exactly what's going on, that's what we call generalized eigenvector. Okay, so if you know you got only one, so this P is really unknown right over here, okay? So how many more do I need? It tells you how many power you have to go more. So yes, you don't care about what is the second power if you know you need the cycle of or basis of 4 dimensions. So then you just forget about the second one. You just square it. You can cube it, and then you that's where you need to stop, because how many more do you need? It gives you how many power you need to go. So remember, if your matrix is going to be size of what was the size of matrix? Okay, so your size of matrix is going to be 4 by 4, right? The chance to get one free variable is just really same as you get 2 free variables, same as to get 3 free variables, okay? So, but seems for this one, you got only 1 free variable. How do I know if I get just really this one only 1 free variable? Because I got already my Jordan Canonical Form. The form of Jordan Canonical Form right over here, it gives me, it seems I got only 1 free variable, okay? So when you get only 1 free variable from these steps, again, yes, I know I need the 3 free variables. I'm pretty sure I won't get from the second power, I won't get from the third power. Sorry, I will get from the third power, okay? So that's just really clear for me, because the size of matrix is 4 by 4. I already get 1 free variable, I have to go to the third power. Does it make sense?
Yeah, that will be your initial vector, which is always an eigenvector, right?
Yes, so you could just really, yeah, it was possibility for some problems to get 2 free variables. Then you go to the second power. How many more do you need? That's just really how many power you have to go.
Okay, thank you.
Okay, so how much time do I have? Oh, no more time. Yeah? I thought I can. Okay, so that's great. I have to stop right over here. I have had 2 examples to practice the process from the initial, really from the blank. I wrote these problems because that was just really wrong process and right answer. But for the 2 next problems, my plan was just really try to do every single step and do it. That's why you don't see over here. So for now, I'm going to stop here. But if you have any question, I'm here. So Solomon doesn't have time, so I will just answer this question next time. But what I need to really right now, let me just stop recording. What I want you to do for me, I will send a really Google sheet. Okay, so simple Google sheet